Hello, this is week 11, and we're going to be discussing statics and dynamics. And so, and statics is a situation where everything is static, which means it's not moving. Our word stationary comes from that. And in this context, everything has a force on it, for example. At least gravity is always working, so if something has no force on it, it's not moving, not accelerating, then the forces on it have to balance. That is to say, you have a downward force of gravity, but you have the upward force of the floor, for example, okay? And so you're sitting in your chair and you're not accelerating, okay? And that's because the two main forces on you balance and add to zero, exactly zero, by the way. So that's static. And so the building of bridges is an excellent example of statics. So bridges are static structures. They better be static because you don't want bridges to fall down. This is the subject of civil engineering: bridges, dams, building, and other large structures. Okay? So that's the main thing we're going to do this week, the building bridges. In dynamics is when there are forces acting. Okay? And the objects are accelerating, potential energies are being changed. This is a dynamic situation, all right? So we'll look at a couple of videos of the so-called egg drop experiment. But I don't think it's realistic to do an egg drop in an online class, because in order to have fun at it and do a good job, you need all kinds of things, like cotton, parachutes, all kinds of, pea gravel, and so on, packing materials of all kinds, and so on. So I think that's not realistic. So I decided we won't do it, but you can watch some videos. There are lots and lots of videos out there. I've looked at a lot of them, and most of them are not that good, but there are a couple maybe worth watching. Okay. Our word dynamics actually comes from the Greek word dynamic, which means, and the word dyne is the root for the word force. Okay, so this is going to be week 11. By the way, let me comment. I really enjoy the videos that you do and that I watch, and I'm not completely finished with even last week's. Okay, but I'll get to it. Don't you worry. Okay, so let's look at some pictures. A discussion of bridges and structures. Here, for example, is an aqueduct. It's a Roman aqueduct. And after 2,000 years, it's not going anywhere. It's perfectly stationary. And it's a remarkable structure. I mean, the Romans were superlative engineers. It's not clear how much they understood. They probably understood a lot, but they didn't have algebra, certainly didn't have computers or calculating devices of any kind. So a lot of it was, you put your thumb up here, and it should be about this big, and then they'd make better measurements and so on. But in any case, to build an aqueduct like this, which goes from the Apennine Mountains into Rome, which is two couple of hundred miles, perfect. This is a remarkable feat. Okay, so that's an aqueduct. Now, I've gathered together some videos. The bridge building videos are here. There's the first one here, YouTube. These are actually all YouTubes. Okay, there's a simple bridge here, and then there are a couple of intelligent discussions of bridges. So if you want to know how a technical person, an engineering student, for example, might talk about building bridges and so on, you can watch the intelligent discussion video. And here's an engineering discussion of truss bridges, truss bridges and structures. And so we won't build a truss bridge, but we're kind of using trusses when we use triangles. So these may be useful for you to watch to give you some ideas. Now, egg drop experiments, there are three of them, actually two egg drop experiments here, and some of them are a little crazy, okay? But in any case, someday you may make your own egg drop experiment video and post it on YouTube. The bottom one is dropping a rover on Mars, and we'll play this one later on, okay? It's a NASA simulation of landing a rover on Mars. So, back to our arches and domes. Again, on the upper right is it's an aqueduct. This one's in Spain, actually, and arches and domes are basically arches, like in the aqueduct here, but turned around in a circle. Okay, so arches are here and domes are here. So this is the Pantheon, for example. Two images of the Pantheon. and it's still standing today. It's the largest unreinforced, shall we say, old-fashioned concrete structure in existence. It's again a beautiful engineering device, and again all of the forces add to zero throughout this entire structure. Okay, so what kind of bridges are there? There's a beam bridge here, and that's kind of, in some sense, what we'll be doing, a simple beam bridge. A couple of posts, for example, to hold it up in the middle and so on. And then below that is a truss bridge. It has lots of triangles in it. So truss bridges are usually used for railroads, locomotives. And you don't care how beautiful it is. It better be very strong, though. Okay. Yeah, Cantilever Bridge is here. Up at the top is an arch bridge. Okay. And then the suspension bridge. The suspension bridges may be beautiful to build, but you know, you would have strings, lots of strings and vertical strings and the suspension and so on and so on. It could be a nice project, but it's complicated. Then a cable stayed bridge here. Is it okay? But anyway, here's the photograph. This is a suspension bridge here, and an arch bridge. Okay, actual bridges. Okay, so now it's there's an engineering solution. Again, at the bottom is a model of atoms in a solid. And as I said before, that curve, the energy function between two neighboring atoms, is a kind of a U-shaped. Okay, and at the very bottom of the U is the separation of the two atoms, and that potential energy function corresponds to a force which is just like the force of a spring which you compress or stretch, exactly like the springs that we used when we measured masses, for example, or when we made a clock, okay, an oscillating clock. Exactly the same formulas apply. Okay, it's remarkable. So from this simple model of atoms in a solid, you can derive many properties of materials. Okay, now one of them is that the strength of a beam, for example, the strength of a beam, like, you know, here's our ruler. The strength of this beam against the deflection in the middle depends on all those springs. Okay, and so for example, here it is, and I can, if I put a force in the middle, I can bend it, right? It flexes down. It flexes down, right? Okay, and in this direction, it doesn't flex hardly at all. Actually, it's very strong, and this has to do with the thickness. How many layers of atoms and springs do you have here? And the strength goes like the cube of this thickness. So this is kind of illustrated in this drawing. Here's a beam on the left, and where the beam is flat like this, the beam has the thickness T. You put a force on it. It could be just a mass, so the force on it is mg, and it'll bend, it'll flex. But if you turn it sideways on the right, so now the thickness is T is much larger, you put a force on it, it doesn't bend. Okay. Now, so to give you an idea, the force goes like the flex, the force keeping it from flexing, I should say, goes like the cube of the thickness. So 1 cubed is just 1, but 10 cubed is 1,000. So if this on the right, when it's oriented vertically, if that's 10 times the thickness, then the strength oriented vertically is 1,000 times the strength in the flat position. Okay, and that's a fundamental principle of civil engineering. Okay, all bridges, all homes. In fact, there's if you're in a dorm or maybe in a modern home or apartment, you may not be able to see this, but if you usually go into the basement of a building or a home, you'll see the beams. And what you'll see is all the beams are oriented vertically, like on the right hand side, because they're holding up the house, right? They're holding up everything in the house. So they're oriented like this, and they're very strong. Okay, so here's a video, and let me start this up. This is where I describe making bridges. Okay, so this is for you to watch.
Bridges, skyscrapers, everything.
So here's a plastic ruler, maybe what you have, and you can see it's a very thin piece of plastic. It's a millimeter. It just flexes like this. It has basically no strength whatsoever in this direction. If I were to take one of our quarters, or let me take, for example, a 50-cent piece and put it on here, and okay, I'm not going to go too much into this, but if I just see if it'll hold up a 50-cent piece, well, it sags inches, okay? So it can't even hold up a 50-cent piece. On the other hand, if you take this and turn it vertical like this, it has huge strength. If I try to push it down in this direction, it just doesn't go. It may try to twist and flop, but the strength pushing down when it's like this is like 1,000 times stronger than like this, okay? And it goes, the reason for that, it goes like a cube. It's an engineering problem. Actually, you can figure it out from that potential energy curve between neighboring atoms that we have in the textbook, and which I've shown you, and I'm not going to drag it out again, but atoms next to each other act like they have a spring between them. And you can go through the calculation and ask what's that springiness. Well, here's the springiness in this direction, but the springiness in this direction is very hard, very tight spring. And it goes like the cube of this thickness. That's the strength, the cube of this thickness. Now, this is a very, very thin, has no thickness at all hardly, so the cube of that's really small, so it has no strength. The cube of this is huge, has very large strength. Now, here's our 30 centimeter, 12-inch steel ruler that we've had from the beginning. Same thing, by the way. It's stronger than plastic, so sure enough, it'll hold up more, but it still flexes. It flexes. Maybe it's 100 times stronger than the plastic. In this position is 10,000 times stronger than the plastic. It's huge, okay? It will not flex at all. So that is the basis on which we will build a bridge, for example. So how do you build a bridge? Well, you can Google this, and there are some photographs in the textbook, for example. And so I started out with, something like this. You want to have, and then, oh yeah, by the way, the ground rule I made for myself is to use simple paper, okay? Now, so these are just strips of computer paper, which I used a pair of scissors, and I just cut them up into, 11-inch long, 1-inch wide strips. So I made several of these. And now, you can, of course, take the manila folders in your box, in your physics box, and you can cut up manila folder strips. Now, manila folder strips are stiffer and heavier than paper. And it works better, by the way. In fact, I've learned this evening that it's much better to use manila folders rather than simple paper. Paper is, of course, extremely weak. Let me get one. Here you go. Here's a paper strip. Here's a paper strip, 11 inches long, inch wide. I just cut it up with scissors. This paper strip is, of course, weaker than the plastic ruler. I mean, the paper strip will hardly even hold itself up. It's so weak, okay? So here it is, right? I try to pull it up from here. It's so weak. So how do you build a bridge, a strong bridge, out of something so weak? Well, the answer is you play the same trick. You orient the beam, it's called. This is called a beam. Orient it this way. Then you have to have something to keep it vertical so it doesn't fall over like this or twist or something. The trick for doing that is to put a sort of a corrugation on it like this. So that's what I did. So I took another piece of this, and I kind of made a zigzag. Okay, in other words, I made triangles, by the way. I made triangles. And then I both tried to tape these down, and I also, for this case, I used a stapler. Okay, I used a hand stapler to put staples in this, okay? And so on. And I didn't finish this one because it was kind of hard. And then I had the other problem is after I get this side done, how do I get this other side done, right? Because you have to have one on both sides like this, right? So I'm trying to do something like this. So I gave up on this one, okay? So then I thought, well, maybe if I have something like this, and then I have a flat, so it's not just triangles, but it's more like a trapezoid or a truncated triangle. And then on these flat regions, I can put a tape. I can just tape it down with our plastic tape. And it worked okay, but it's really not very good It's not very uniform, and it wasn't any fun for me. So I gave up on that. Then here's another one. I kind of brought this one to completion. In other words, I did one whole thing, and I have them taped. I used tape, and then the problem still came. How am I going to get this other side on here? And you can think about doing that in a classroom, for example. If you have, for example, super glue, you could just go down here and just do a dot of super glue on each one of these and just hold it in place. It'd be great. Okay? I don't have super glue. So again, I've tried several things, and none of them work very well. But in the classroom, of course, that's the way actually science and engineering often is. That your first models that don't work very well. You have another idea. You try something else. So I tried something else. Instead of these kind of small triangles, well, let me emphasize, by the way, on the question of a triangle here. If you have a triangle like this, here's a triangular. If you push down on it, apart from the paper flexing, it doesn't collapse. It doesn't collapse. If you had a square frame, and push down on it, it could easily collapse. Either way, it could collapse. But a triangle will not collapse. So a triangular structure in anything, like a building or a bridge, is really very important. And you'll see, by the way, here in this in a recorded lecture, you'll see the Trestle Bridge. Basically, is a whole bunch of triangles all welded together. Okay, very strong. So I made the triangle structure a little bigger, and then I used staples. I used staples when I could, and I used tape when I couldn't use the staples. Here's a staple holding that in, and a staple holding this in. Okay, so on the ends I could get the stapler in the staple things, and then okay, so now I have two beams. Here are the two beams, and here's the triangular structure to keep the two beams vertical and parallel to each other. And then I also needed something. I needed something to keep it from, flexing out here. So I taped on the top decking. Okay, so I taped decking on the top here. Okay, so that's it. So here's my bridge. So how do you know if it's a good bridge? Well, first off, I want to do something like I want to weigh the bridge. I mean, this is a very lightweight bridge, of course, right? And if you were doing an engineering, for example, in 5th or 6th grade, and you wanted to emphasize engineering aspects, you could ask students to build the lightest possible bridge so that it would therefore, for example, be the cheapest possible bridge. And so maybe having a lightweight bridge is a good idea. So if I weigh this, and then you weigh this on your very, very nice, on your very, very nice electric scale, electric balance. This bridge weighs 4.21 grams. 4.21 grams. Okay. Simply paper and tape. A couple of staples. Okay, so now how much weight, how much mass will this support before it collapses? Now, in the building bridges, for example, around Iowa, there's a smaller bridges around Iowa. You'll see that there's a limit. They posted so many tons. If your truck weighs more than so many tons, you cannot go across this bridge, because that's the failure point of the bridge. More than that, it may collapse. Actually, that number is probably 3 times the failure, because of the factor of 3 for engineering, safety, and so on. So in any case, let's see how good this bridge is. And I'm just going to use our piece of PVC pipe. I cut off a piece of it for something else, and our little block right here, okay, that we used previously for our ramp. So you can use, for here actually, you can use a couple of books or a couple of anything, by the way, just, okay. Now this is a bridge span of more than 10 inches, okay? A little bit more than 10 inches. So, what can it hold up? Well, okay. Holds 1/4, no problem. So let me just keep on piling on quarters. And, oops. I'll lose my money here. And you can see it's not flexing. I mean, it's flexing a little bit, as any structure must flex, but it certainly doesn't look like it's going to collapse. So let me just keep on going. This is 2, 4, 6, 8. That's 9. That's 10, 11, 12, 13, 14, 15, 16 quarters, 16 quarters. If I put on a 50-cent piece, that's 2 quarters. So did I say that's 16 or 18? Anyway, that's 60. So that's 18. And a 50-cent piece, 4. So this is 22. 22 quarters, and it hasn't budged, okay? Now, I can fish through here, and we can put more and more quarters on, okay? And I guess I'm not going to go through that. That's 22, 23. I'll go to, say, 25 just for fun. And I need more quarters. Okay. Okay. 24. Well, there you go. That's the collapse. So 24. Actually, there was a weak corner here. If I had been a little more careful, I could have avoided that. But anyway, it'll hold, what was it, 23. Let's say 23. I forgot exactly. That's how good this bridge is. 23. What is that? What's 23? Well, let's figure that out. Let's go 23 times the mass of 1/4. 23. Okay, a quarter. Okay. 5.68 grams. It's 1/4. So that's 130.6 grams. 130.6 grams. So let's divide that by the mass of the bridge. It's 4.21. And that is 31. So this bridge holds 31 times its own weight. Now that's a strong bridge, just paper here, okay? 31 times. Now, and now if you work on this, man, you may find more clever ways and so on, and better techniques and so on, and make it even better. But that's a pretty good starting point for a bridge, for a simple bridge. So I would encourage you to try to build shall we say, a high-quality bridge like this, but maybe you do a better job than I've done, and so on. And this only has, say, one bank, okay? One could build, the best thing would be to have another bank over here of this, right? So you have 1, 2, 3 beams here instead of just 2 beams. And then with the same, you have to do the same zigzag here. That may, in fact, be difficult. I encourage you to find clever ways to do this, okay? Or find clever ways for children to do this. Then that would be even stronger, okay? With not that much added weight. So you might even do better than 31 times. Okay, so now I think in the recorded lecture, also in the text, there's another simple thing shown. You just take 8.5 by 11 paper, and you just, fold it, fold it back and forth, and you get just this, okay? It's like an accordion, by the way, just an accordion. And then in order to keep it from falling apart, I did the same thing as I taped a top onto it, okay? So that gives you, the top gives you something to put the coins on. It also gives it a little more structure. So this is the simplest thing. There's no other piece of tape in here. There's nothing fancy like this, okay? It's just sort of simple. So let's see how well this bridge does. Here. Okay, here. And it still actually flexes apart and so on. It's maybe not so great, but let's start piling on our quarters again and see how good it is. So that's 4, 5, 6, 7, 8, 9, 10. This makes 14. This makes 16. And here's 18, 20, 22, 24. It's even doing better than the fancy bridge, okay? Now, in order to qualify as a good bridge, one would have to, shape this up a little bit and so on, but there you go. Now, just for fun, it's always nice to test something to destruction. That's what is actually done, by the way, with automobiles. You build an automobile. It's a beautiful device. It's lots of safety features and so on. An automobile company will run a car into a wall, of course, a dummy inside of it, to see where it fails. Where is the failure in a car that hits a wall? So I'm going to try to test this until it fails. I don't want to put more coins on. This just takes too much time. Let me just push down on it here. Well, I'm going to tell you, I'm pushing. Okay, the failure is over here. It starts failing over here. If I do this more, is it falling off the edge? Yeah, the failure is over here. There you go. Okay, so that again is comparable, maybe even slightly better than the fancy bridge. So, there you go. I encourage you to have some fun, because this is something the kids can do day after day. You can make bigger competitions. This is just a, for example, a 1 foot bridge, like an 11-inch bridge, for example. But you can make more challenging things. For example, how about 3 feet? Can you have a team of students build a 3-foot bridge, 3-foot long bridge? Or an arch bridge. This is like a Trestle Bridge, but an arch bridge that has an arch in it like this, okay? Like a Roman arch. So from this bank to this bank, and then with a roadway in between, shall we say. Or suspension bridge, like the Golden Gate Bridge, and so on. There are lots of bridges. And so this is the subject of statics. And so all of the buildings on campus, and the building you're in now actually was designed with computer codes, very complex computer codes, in which every point inside, every point of the structure, every point where something, one beam is attached to another fixture, every point in the structure has a net zero force on it. Net zero force means it's not going to accelerate. So it's going to stay static, okay? And the reason why we got a collapse is that there was a part of the structure which did not have enough strength to withhold the so-called gravitational load, or my poking at it. It's strong. So that part weakened and it accelerated and it fell down, okay? So that's statics. So, thank you. Okay, so now afterwards, I weighed the corrugation bridge, okay, the simple bridge, and it had a mass of 6.41 grams. And actually, so in other words, 50% heavier than the fancy bridge. So I'm not sure, we never really tested the second bridge, the accordion bridge, I'll call it, to destruction, because I was poking it. I was actually poking rather strongly. And so, maybe these two are comparable. The accordion bridge actually was an 8.5 by 11 piece of paper, which I just folded like an accordion, okay? So there's a lot more paper in this bridge than there is in that bridge, okay? So I mean like 50% more paper, okay? So now, and then actually here's a photograph of the beginnings of a paper bridge, and showing the materials you need. A stapler is good, something to take and tape, and scissors, and so on, okay? Again, I would say that manila folders, especially offices, often have boxes full of used manila folders, and they're just fine. You can cut them up, and they work much better than paper, actually. Although paper's more challenging, of course, right? Now here's an arch, okay? This is somewhere, I think, Kansas City, I'm not sure. And here are other arches, okay? They're also static structures, and of course the Romans were great at arches. And the bottom one is an artistic arch, okay? But notice at the upper left, for example, the stone in the very middle is called a keystone. And that's actually a phrase in English. Keystone is that one small piece which holds all of the rest together. You take out the keystone and the whole thing falls down. And indeed it does. So that's the keystone of an arch bridge. And there's the keystone in the second figure. It's also noted there as the keystone, and so on. So here's a comical keystones, comical arch structure. These big cubical devices used to be probably maybe when you were born everywhere. Your iPad is probably 1,000 times more capable than each one of these, and the value of each one of these things is now less than zero. You have to pay people to take them away, but these actually were once upon a time computers. Okay, so that's a joke. And here's a blackboard discussing some of the things that would be done in this class, for example, and a figure of merit. Okay, how much a bridge. I won't do that; it's too complicated there. Now, so that's building bridges, okay, and a great thing to do. And that's all you're going to do this week, okay? Now the egg drop experiment, the egg drop experiment is dynamics because there's a lot of forces. I mean, there's gravity and things are falling down and they're hitting the ground and so on and so on. Very complex dynamic situation. And this is an example of a stopping problem. How do you bring something to a stop without breaking it? Okay, that's a stopping problem. Now, this is actually the egg drop experiment. I think was originally an engineering college competition. And I think they still go on today with much stringent requirements than we impose. For example, we do it for fun, basically, but it's still a very good problem. Examples of stopping problems: you want to stop a car on the street, so you have brakes and you have friction force, and it's the friction force that slows you down. Bringing the space shuttle out of orbit onto the ground is another stopping problem. When the shuttle is in orbit, it's traveling at 18,000 miles per hour. At some point, you have to get the velocity down to zero so that it can land at an airstrip, okay, in Florida. That's a stopping problem, very serious stopping problem. Crush zones in cars solve a stopping problem for when your car is in an accident. Why do you have seatbelts? Helmets, for example, for athletes, in particular football. It's a stopping problem, okay? You want your head, when it's hit hard, when your helmet is hit hard, you want your head to slow down and stop gently, okay? Otherwise, damage can be done. Landing the Mars probe, that's another problem of a stopping problem. And also, by the way, when you jump off of a table or something, you jump and you land on your legs and you roll, okay? And that's a way of lowering the force that your bones and your muscles have to absorb. You know, jumping, landing, and rolling is a trick that all athletic kids learn. So now the whole point of a stopping problem is what's called the work energy theorem. And so you can look through this, and I'm going to go through it because I think it's important physics, actually. All stopping problems start with some mass at some velocity, okay? And the kinetic energy is 1/2 m, 1/2 the mass of the object times its velocity squared. So this could be a car on the road. That means it has some mass, a couple of tons, has some velocity, 60 miles an hour, for example. That's all kinetic energy. When you want to come to a stop, you're going to have to act with a force. And the force will be the friction force of the tires on the road. Okay? And that friction force is going to have to act through some distance d. And that distance is going to be called the stopping distance. Okay? That's the distance, shortest distance you can stop in, actually. And the force times the distance is the work. And work has the same dimensions as energy. So in order to bring the kinetic energy down to zero, you have to do an amount of work which is equal to the kinetic energy. So the force times the distance has to equal the kinetic energy you start with. Okay? So now here's the formula down two-thirds of the way down. 1/2 mv squared has to equal the friction force times the stopping distance, d. Now, if you have a car at velocity v, 1/2 mv squared is a fixed number, okay? And the only way out of it, without making the force any larger, is to make the d as large as possible. So that's the point of for example, crush zones in cars, or helmet padding, for example, or the stopping distance of a car. Another thing to keep in mind about this: if you're speeding and coming across a red light ahead of you, then your stopping distance, the friction force is the friction force, and sometimes you can't do anything about that. You can apply the brakes as much as you like, but the tires on the road determine what the friction force is going to be in the end, right? And so the friction force is kind of fixed, okay, for a car on the road. So your stopping distance, d, is the distance it takes for you to stop. Notice, it goes like the velocity squared, which means if you're traveling at 60 miles an hour, it'll take you so long, a certain distance to stop. If you're traveling at twice that distance, at twice that velocity, the stopping distance is 4 times as large. 4 times as large, okay? So that's why you keep your distance on a freeway. That's why you should always be cognizant of how fast you're going when you may have to stop, for example. Now, this formula, that bringing the using work, force times distance, to take the kinetic energy of 1/2 mv squared, taking it down to 0, you can play with the friction force and you can play with the stopping distance, okay? But the product of the two has to equal 1/2 mv squared, okay? There's no way out of that. But to make the problem easier, oftentimes a smart thing is to make v smaller first. Try to reduce the velocity first, and then apply your friction force, and then consequently stop in a distance d, okay? So there are many ways to do the stopping problem here, and so let's take a look at some photos here. One way to slow things down is to put your egg, your package, in a bundle of balloons. Okay, so now the balloons serve two purposes. You drop this off of a 3 or 4 story balcony or whatever, and the balloons act like a parachute and they slow down the velocity. So the velocity is already small. And then when it hits the ground, the balloons act like a cushion. Okay, and so the egg is quite safe. Here's another one of one simple balloon. The upper right, that's a parachute. Made out of basically just a grocery sack. Okay, the simplest possible parachute. You can do very fancy parachutes, but that's a simple parachute. Here are other gadgets, to try to slow things down. Here's a wedge structure. You put the egg inside of there, and then you have this kind of flat thing, which again acts kind of like a parachute. It retards this velocity, slows it down a little bit, and so on. And now here is a Mars. How do you land something on Mars? So when you're on your way to another planet, you have to get up to a relatively high velocity, like 20,000 miles an hour. It has to be more than orbital velocity, which is 18,000 miles per hour. So maybe it's 20 or 22,000 miles per hour. So now when you get into the gravitational field of another planet like Mars, you start getting sucked in by gravity of that planet, and so you start going faster and faster. But now you have a delicate probe. I mean, you have a little, whatever, you have your Martian probe, which you want to survive. You want it to work after it lands. So how do you possibly land it? Well, it's a stopping problem. And so here's a NASA animation of that. This is the probe, and it separates from its casing as it comes in. It gets into the Martian atmosphere, and the Martian atmosphere is rather thin, actually, thin compared to Earth's atmosphere. So it develops a lot of heat on the way in, but that's okay. Now it drops out a parachute. Again, the air is thin, so the parachute doesn't work as well as on Earth, but it slows it down. Okay, slowing it down, there's a friction force, and it goes over a long distance, and now the package now separates. There's a heat shield on the front, and that fell off. The package is here and is tethered back again to this canopy, which is again another parachute. Okay, and it's more than a parachute, as you'll see. It'll have retro rockets in it. Now, the balloons. Let me stop it here. Balloons popped out. Okay, I mean, so in other words, the rover, they inflated the balloons that surrounded the rover. It's the same trick as rubber balloons surrounding your egg, okay? And so here it is. Now the retro rockets fire, and it slows it down even more. And then finally, when it gets close to the surface, they just cut it loose and just let the balloons bounce. So I don't know, there are 20 or 25 balloons here, and inside of there is the delicate package that you want to safely land. This is actually quite smart, because when you're coming in on Mars, you can you don't quite know where you are. I mean, you can I don't know what that noise is. So it's unfolding. The balloons have all been deflated. It unfolds. We can stop this now, actually, because the landing has now taken place. And but I'll just let it go, because now you can see the wheels here, because it's going to be touring around. And then it opens up, which are probably solar collectors, so it has some power. And it's unfolding. It'll want to unfold some antennas also. And so it can communicate with Earth. And it's going to want to bring out its cameras and start taking photographs and so on. Okay? So I think these are the cameras coming out. I'm not sure. Take a good look around. Looks like Death Valley. Okay, so that was landing a probe using the work energy theorem over and over again. Parachutes, thrusters, balloons. Okay, so fine. Here are some tips for the egg drop experiment. This is just for your future reference. Okay, yeah. I don't really think it's practical now to do an egg drop experiment. In the in-person classes, we would go to the molecular biology atrium, which is an indoor atrium. Is really great. You can take the elevator up to the 4th floor, and then at the bottom, the atrium is a ceramic. I mean, it's hard, very hard surface. Dropping from 3 stories high, the velocity gets up to 60 feet per second, so it's a high velocity without any retarding. And then you just have to watch for pedestrians in the atrium and so on. So anyway, the whole class goes over, and it's kind of an hour of fun dropping your egg packages off. Okay, so thank you very much. And then I will be at the Zoom session on Monday at 3:20 p.m. Okay, ask any questions you like. And if I left something out of here, just bring it to the session and ask your questions in the chat box, whatever. Okay,